Welcome to Math 31, where we are doing an introductory course for calculus. We're in pre-calculus so far. We haven't gotten into the heart of calculus yet. In our previous lessons, we've been looking at limits, and most recently, we came back to the idea of how do we use limits to find the slope of tangent lines and then the equation of tangent lines to functions. And in this lesson, we're going to look at some applications, beginning with looking at velocity and other rates of change. So beginning with velocity, I guess. So as we get into calculus, we typically change the variable that we use for position. Up till now, you might have used the letter D to represent position, but now we're going to use the letter S because the letter D is going to be fairly significant as we move into finding derivatives. And so if position is S, then displacement, which is the change in position, will be delta S. And when we're going to calculate average velocity, that'll be our displacement over a time interval. Well, given these variables for position, displacement, and velocity, I would like you to work through these next couple of questions. So warm-up questions here. Pause the video. Once you finish those questions, please restart the video and we'll compare our answers. We're asked to determine the average velocity between 1 hour and 7 hours. So we can see this on the graph. We have these 2 points. To calculate the average velocity, we will be using that slope formula. So we can do the change in y over the change in x, and we get 118 kilometers per hour. If I was to draw a line that connected those 2 points together, this is what it would look like. And so the slope of this line will be 118 kilometers per hour. So that's the slope at every point along the line, and so that will be the average between these 2 points. Is the velocity determined in question 1 the same as the instantaneous velocity at a time of 1 hour? Well, here as we look at a time of 1 hour, we can see that this red line doesn't match what the slope of the tangent line would be. And so we would have to say that no, the line connecting the distances of 1 and 7 hours is not tangent to the curve at 1 hour, therefore it's not the instantaneous velocity at that time. But let's go on to an example here. Suppose an object moves in such a way that its position in meters is given by this position function. So S is position as a function of time, where t is measured in seconds. We want to calculate the average velocity over this time interval from 2 to 4 seconds. So when we do this calculation, our change in position over change in time will be position at time 4 minus position at time 2, all over the change in time of 4 minus 2. Well, substituting those values into the position function will look like this. And then we want to evaluate. So it's just a matter of number crunching to evaluate and work it out to get the average velocity over this time interval will be 1 meter per second. Well, that's pretty familiar to questions that you've done in previous grades. So why don't you do this check your understanding question? Same idea. We're going to use the same position function, so you can see it up there at the top of the page. And we wanted to determine the average velocity for a half second interval that begins at 2 seconds. Slightly different wording. See what you can come up with. Restart the video once you have an answer. Well, if we have a half second interval, then I'm looking at position at a time 2.5 seconds, half a second after it's 2 seconds. We're told it began at a time of 2 seconds, and comparing that to the position at a time of 2 seconds. Given that half second interval, I know that my delta t, my change in time, is 0.5, so I don't have to do a calculation of 2.5 minus 2 because I already know that from the question. We do the substitution into the formula, evaluate, and there's our answer. And what we're finding is something we can visualize on this graph. So here, the red graph is our position function. So the position that we had up here. And then as we look at our lines, here this blue line is what we found in question number 3. We found we had a slope of 1 meter per second. So that was between our time of 2 seconds and the time of 4 seconds. That was the slope of that secant line. Then for the next question, we found that half-second interval where we went from our x value here of 2 down to this x value is the 2.5. And we calculated that slope to be negative 0.5. Well, suppose we have exactly the same position function equation, and we want to know the instantaneous velocity at a time of 2 seconds. Well, here we're looking for the slope of a tangent line, which is what we spent lesson 1.4 doing. So here I'm going to use formula 2. Formula 2, as you'll recall, is the limit as h approaches 0. I don't have f of x functions, I have s of t functions. So I have the position at a time 2 plus h minus the position at a time of 2. All over h is approaching 0. I can do that substitution into the formula that we're given, substituting the 2 plus h's in for time. And then here, when I substitute the 2 in, my position ends up being a negative 2. And again, that's what we saw in this graph here, that when x is 2, my y value was negative 2. Well, we need to do some expanding, collecting like terms, because we want to be able to find a common factor of h. So here I've expanded out, and we have that binomial being expanded. And that gives us the 4 plus 4h plus h squared. Then we distribute the negative 5 into the brackets to get the negative 10 minus 5h. And then we have the plus 4 and minus the negative 2. As we look to see what's going to happen here, we have this 4, and we're going to be adding this 4 and adding that 2 to give us a 10. Why am I stroking them out? Because here I have a negative 10. So they cancel out with this negative 10. And I'm left only with terms with h's. The 4h minus 5h I can group together because they're like terms. Which leads us to this point where it's actually a little bit further because I was able to pull out that common factor of h. So I have here the h squared, and when I group this and that term together, that'll give me a minus h. Pull out the common factor, and we get our next line. As these two common factors cancel out, this h is going to go to 0 because my h is approaching 0, and I'm left with a velocity that is equal to negative 1 meter per second, and that is the instantaneous velocity at a time of 2 seconds. Let's come back and look at this graph on the previous page. Here, remember the slope of this secant line that we found here, the green line, that was a negative 1/2. And so as we look at the slope of the tangent line, as we look from this point, kind of going sort of like that, I'll imagine that's my tangent line. We'll see how good that is as I move it here. Not great. We'll tilt it this way a little bit more. Looks like that slope negative 1. Yeah, that looks fairly reasonable. Now suppose we wanted to be able to figure out the instantaneous velocity at any point on the curve. So we're going to say t is equal to a, it's equal to some variable, some mystery value. So what we're trying to do is trying to find a velocity function of time. So this time we'll use equation 1. We could use equation 2, but again, just for practice, let's use equation 1 this time. So I'll do as t approaches a, the limit, my s of t minus s of a, all over t minus a. I can substitute those variables into the function that we were given, and this is what it will look like. Now, as we look at this, we can see that this 4 minus this 4 will cancel out. So I'm just left with variables of t and variables of a in the numerator. And I've done a little bit of rearranging. So what I've done is I've grouped the squared terms together. So the t squared and the a squared, and again, it's still subtracting, so that's why I have a subtraction here. And then I have this minus 5t subtract the negative 5a, which gives me that plus 5a. And now I'm going to kind of think of them separately, and I'll factor this first difference of squares, and I'm going to factor the second two terms as well. When I factor the difference of squares, I'll get a t plus a times a t minus a. And when I factor out the negative 5, I get a t minus a. So as t was approaching a, my numerator and denominator were both approaching 0, so I'm looking for a common factor of t minus a, and now I can see that common factor. When I pull that common factor out in front, I'm left with a t minus a minus 5 once I pull that out. So again, I'm taking this, and I'm taking this, I'm pulling it out as a common factor out in front, leaving me with this t plus a minus 5 left over. Well, at this point, we can see this common factor of t minus a, which is the problem factor. So once we cancel that out, then we can do a substitution. So now I can replace this t with an a because t is approaching a. So my t value approaches a, I can just substitute in, and I'll get this as a velocity function of time. And I didn't put it in, but I could have written it in function notation where I had v of t is equal to, well, I guess it wouldn't be v of t, it would be v of a, since I'm using a's instead of t. So any point on that curve, I could determine the instantaneous velocity. So let's do that in a few questions. Here's my velocity equation. Here I'm saying, well, if t equals 0, well, I could say a equals 0. I'm just going to substitute in, maybe I should show an extra step here. I'm going to be doing my velocity is equal to 2 times 0 minus 5, and I get the negative 5. For the next one, my velocity will be 2 times 1 minus 5 will be 2 minus 5, which will be negative 3 meters per second. For the next one, velocity is equal to 2 times 3 minus 5, and I get 6 minus 5 is 1 meter per second. Look how fast that was, finding each of those instantaneous velocities. Let's leap back for a moment and see here on this page, look at all this work that we did to find the instantaneous velocity at a time of 2 seconds. If I, instead of doing all that work for every single different value of time I was interested in, if I could come up with a formula keeping a variable in, like the variable a, once I have a formula, it's really fast for me to figure out some instantaneous velocities. Well, let's look at another type of question. Here we have a stone being dropped into a pool of water. It creates a circular ripple that travels out. We want to determine the rate of change in the area of the circle with respect to the radius at the moment in time when the radius is 20 centimeters. Once again, we'll use Formula 1. So Formula 1 will look like this, where I'll have my rate of change in area with respect to radius. So area as a function of radius is pi r squared. So I have my area as a function of radius minus the area at a radius of 20 centimeters all over the radius minus 20. Again, numerator and denominator will both be going to 0. So I need to be able to find a common factor of r minus 20. Well, let's substitute into the formula. A of r is equal to pi r squared. A of 20 is pi times 20 squared. Well, what do we see here? Well, there's a common factor of pi. So notice that I took that common factor not just in front of the terms in the numerator or of the entire rational expression, but I've taken it way out in front of the limit. This is one of those properties that was displayed on page 13 of your textbook. From way back, we looked at that. One of those properties of limits that we're able to do. Because this is a common factor that doesn't have an r in it, as r approaches 20, that doesn't change this value of pi, so I can pull it out in front as a common factor. Well, now I can see that I have a difference of squares in the numerator. So let's factor that difference of squares, and we can see that common factor of r minus 20, and we can cancel them out. So now, when I replace my r with a 20, I have pi times 20 plus 20, which is 40 pi centimeters squared per centimeter. Now at this point, you may think, well, I can reduce those units, but we don't want to because the units have meaning. Remember that in this question, what we're looking for is a rate of change in area, and our area is centimeters squared. With respect to or related to the radius, and the radius is in centimeters. So we don't want to reduce this because this ratio has meaning. What it's telling us is we have a positive here. So at the instant when we have a 20 centimeter radius, the area is increasing by 40 pi centimeters squared per centimeter at that instant. Here we have it in words. At the instant when the radius is 20 centimeters, the area of the circle is increasing at a rate of 40 pi centimeters squared, which is about 126 square centimeters, for every additional centimeter of radius. That is our instantaneous rate of change. Well, why don't you try the next question? Here we have a spherical balloon, and I've given you a formula for the volume of a sphere. We want to find the rate of change in volume with respect to the radius when the radius is 10 centimeters. Pause the video, restart once you finish the question. We're asked to use formula 2. And again, we want to be flexible to be able to use either formula. So it's good to practice with both. So here we have 4/3 pi times the radius squared. So this is the v of r, or v of 10 plus h, minus the v of 10, the volume at a radius of 10. And it's all over h. As we look at this one, hopefully you saw that common factor, and you recognize that you could pull out the 4/3 pi in front of the limit. Then we had a difference of cubes, and we can factor that difference of cubes. Now I could expand it out, or I could factor it. I can't remember what I did. So it looks like I expanded it out, but I could have factored. Looks like expanding was a good choice. So when I expand this out, 10 cubed plus 3 times 10 squared times h, 3 times 10 times h squared plus h cubed. So again, binomial theorem could be used in order to factor this out. And again, that line from Pascal's triangle, which is the 1, 3, 3, 1 line, those are the coefficients from Pascal's triangle. The first term, the 10 cubed, squared, exponent 1, exponent 0, and the h's to the exponent 0, exponent 1, squared, and cubed. So binomial theorem can help us expand there. And we see here that these 10 cubes cancel out. All of our terms have h's in them still, so we found that common factor of h that we can pull out. So there I've pulled out the common factor of h. The common factor can cancel out, and then any leftover h's are approaching 0. So this is going to 0, that is also going to 0, and we get 400 pi cubic centimeters per centimeter. And again, we don't want to reduce the units because the units have meaning as they are. Here we have some more check your understanding questions. So I'll have you pause the video, finish off the questions on this page, 10 and 11. Once you've finished both, restart the video to compare your answers with mine. Here we go with Formula 1. When t is equal to 3 seconds, I have s of t minus s of 3 all over t minus 3. I can substitute in the numerator into the formula that we have and do some simplifying. When I simplify down, I get t squared plus 8t minus 33. Again, I'm looking for a common factor of t minus 3, so if I'm expecting a t minus 3 in my numerator, so here I'm expecting that this is going to have a t minus 3, I can use that factor to make it easy to find the next one. T times what is t squared? T. Negative 3 times what is negative 33? Positive 11. Double checked, I multiply the outside terms and I get 11t. Inside terms, minus 3t, that gives me this positive 8t. There we go. We can see the common factor that gets canceled out. So this cancels with that. My t approaches 3. 3 plus 11 gives me 14 meters per second. Finally, question number 11. Now we want to find a formula for the instantaneous velocity, and this time I've encouraged you to use formula 2. Here we go. Remember that this formula said I was looking for the limit as h approached 0 of s of a plus h minus s of a all over h. So that's what the formula would look like using the position function. Here it's substituted in. So that was my time squared, 8 times the time plus 9, a squared, 8a, and plus the 9. When I expand and look for like terms to do some simplifying, I can see that here I have an 8a and a minus 8a. Oh, there I had an a squared that I jumped right past and a minus a squared. Here I have a 9 and a minus 9. And notice that every term in this second function canceled out. We're always going to expect to see that. So whatever we get here, we're going to look for it earlier on to see where that will be able to cancel out. And notice what we're left with. We have a term with an h, a term with an h, a term with an h. So we can see that we have that common factor of h. There we have it pulled out, and we can cancel out those h's. And then we end up with this equation because this h is going to 0 because our h is approaching 0. So we have 2a plus 8, and our units would be meters per second. There we go. That's the end of this lesson. Time for some practice. Enjoy.